Welcome, I'm Mike, a Googler, a statistician, and I'm passionate about learning and sharing. Today, I'm a friend, and I welcome you to my office. This is a series of videos that follow a GitHub repository. That repository is full of notebooks. Those notebooks encapsulate workflows, end-to-end machine learning journeys. We described them as fingerprints earlier, where different people for different purposes have different ways of doing them. I've collected these from friends, from customers, from coworkers, and from my own curiosity throughout my career. Today's video, we're in notebook number 01. It's where we create the data source. We're not quite into the workflows yet, but we are at that point where we're creating the data that's going to feed all of those different variations that we're about to use. I'm going to share my screen. We're going to start directly from the repository. We're going to retrace our steps into the notebook, and then we're going to run notebook 01, and we're going to talk our way through it and explain some of what we did and why we did it, and do a little Q&A along the way. Sound good? Let's get going. All right, so here's the repository. The intro video is directly linked from there. We've done notebook 00. That's the only prerequisite if you're running along side by side. It creates a Google Cloud project. It creates a notebook instance in Vertex AI that we host these notebooks in. If you just want to follow along, you can click notebook 01 directly here. But we're going to do it live in Google Cloud. So to do that, we start with console.cloud.google.com. Once we're in here, we want to go to Vertex AI. And under Vertex AI, we're going to go directly to workbenches. That's notebook instances. So Vertex, workbench, and we created one in that last video, the setup video for notebook 00. We're going to see that listed here. And we're going to click Open Jupyter Lab. Now we've already cloned the repository in here. We've even run notebook 00 in that previous video, so we can just immediately open notebook 01 called BigQuery. I'll explain what that is also. Table data source. Okay, we don't need this widget that it's asking about. We see our repository here, open notebook 01. All right, and it shows prerequisites, the only one at this point, 00 environment setup. This is the video that you're currently watching. Coming in, what resources are we using? So Vertex has all the pieces we can use to create workflows. In this case, we're in a notebook instance, starting there, and we're going to interact with that file we put in Google Cloud Storage. We're going to move it into BigQuery. We're going to review it, take a look around, talk about the data, and then we're going to prepare that data for machine learning work that we're going to do later on. That workflow, in Vertex, we open the notebook. Here's that instance. This is like Inception. We're looking into what we're looking into. And as we do work with this, since we're using BigQuery, that's another Google Cloud product, we're going to hop over there occasionally and take a look at the assets that we're creating there. Assets being tables, rows and columns, and a structure that we can view. How do we do this? We need source data. This source data is one that's been used in machine learning challenges before. It's a fraud data set. It's currently stored in BigQuery's public data sets. There's a massive library of just amazing data for a number of purposes out there. We've chosen one that's commonly used in ML competitions. It's called the ULB fraud detection table. It's a table of credit card transactions that are labeled as, there's a column called class, that's our target. It has labels. Class is 1 or 0. 1 means this is a fraudulent transaction, and 0 means this is not a fraudulent transaction. It's a normal one. There is a link here where you can go review a lot more details. I'll give you the most important detail that we have here. The columns aren't things that we would think of, like maybe the age of a customer, or the location of a customer, or location of the transaction, or the store where the transaction took place, the amount of the transaction. A lot of that information could release the ability to uncover who a person is, and that is a privacy concern. So to do this competition, they've taken a method of taking many columns and condensing them into fewer columns called principal component analysis. It's a restructuring of the data to maintain variance information about it with fewer measurements, features of that data. Those data points, those columns, they're going to be orthogonal to each other, uncorrelated. And they just have general names like V1, V2, up to V28. We don't have interpretations for these. The numbers in them, they're scaled. They're not going to be things that are useful to us. So we just have to view them as, these are features, these are measurements, this is good info, it contains information. Can we use it to understand whether something's fraudulent or not? And how well can we predict fraudulent or not from that information? All right. There are 284,207 of these transactions. Let's jump down into it and take a look at it. So first, just like you, I'm running this in a new project, not the one it was created in. So I have to change that one variable. We are working in StatMike-demo3 project. We'll keep all the others the same. These are just parameters we set to get reused throughout the code. We're going to be working with BigQuery, so let's load that module, google.cloud.bigquery. Let's create a client into that, authenticated to this project, StatMike-demo3. And since the word bucket in Google Cloud Storage, that name, we've made it identical to the project name. Let's just make a variable that's equal to that variable. And now, the way BigQuery works is you have projects. Projects then have this next lowest level, these buckets. They're called datasets. They organize information. And then we need to create one of those. And then inside of datasets, you include assets, and the most common asset is a table, rows and columns. We're going to load one of those in from that Google Cloud Storage file. So let's go through that workflow here. Creating the dataset. The language of BigQuery is SQL. Later on, I'll describe more about BigQuery, but let's just go, it's a data warehouse. So you interact with it using the common language called SQL. I think that's structured query language. We're in Python using a client to BigQuery, so we're going to send our SQL messages as like little packets, little text strings over there, and let them run, and so that we're offloading the work to BigQuery from Python. Python's just our orchestrator or interactive environment at this point. So we're going to define a query, and this is going to be a text string formatted to include a variable, that project ID. And what we're going to say is select schema name from, we're already looking at a cool concept in BigQuery. The project ID has this view that's automatic called the information schema, and it has a table in it, or a view in it, schemata. It includes all the information about tables that are in a data set or in a project. So we're going to run that. And the reason why we're going to run that is we may have already run this project. We're going to check that list of data sets and tables in the project, and we're going to say, if the one we need, the one we're trying to create, doesn't exist, create it. And if it does exist, don't recreate it. The way we do that is we say, this is back in SQL language, create schema, if not exist. This is going to be the project, StatMike-demo3. The data name, I believe we called that fraud up here. Data name fraud. Options are do it in the region. We're using US Central 1 for everything in these. And I'm going to create a label just so I know where it came from. It came from this notebook in my project. That's just a piece of information you can use to tag and search things. We're going to run that query in BigQuery and grab the result. The result will just be, hey, it finished. We can grab aspects of that job. A number of pieces of information get attached to it, like when it ended, when it started, and we can use that to calculate how long it ran. So that little job ran for 0.66 seconds. We didn't really do anything there. what we've done is we've verified there's a data set there. Let's go take a look at that real quick. So back over here in Google Cloud, let's go to BigQuery. It's going to be our home for today's session. And we're going to see the ability to explore that hierarchy we talked about. We're in project StatMike Demo 3. There's StatMike Demo 3 for BigQuery. Inside of there is a data set called fraud. And inside of fraud, there's currently nothing. Let's load our data set into a table inside of there. So the next step is going to do that. It's going to define the pieces of information to orchestrate that operation of grab the CSV from Google Cloud Storage, bring it into BigQuery as a table inside that data set. The way we do that is we tell it, well, where is it going? Destination. Destination is going to be BigQuery, a table reference from a string. Now that string is that 3-level piece of information: project, dataset name, table name. So it's going to land there. The job that's going to make it land there, it gets a configuration. It's BigQuery, a load job config. We're going to say write truncate. If the table's already there, what do? Do you overwrite it? That's what we want to do. Do you append to it, or do you not allow it to do anything? Our source format, in this case, BigQuery source format is a CSV that's sitting out there in Google Cloud Storage bucket. We want it to pull columns in, but columns could be strings or integers or floats or long floats or really long integers. It could be times or dates or time dates or date times. It could be geography coordinates. It could be a number of things. So we could tell it, we could feed it a schema if we wanted to list it for all those columns. Or a cool thing we can do is we can say auto detect equal true, and it'll kind of scan the column and go, I think it's an integer, put an integer, it's a float, put a float, a string, and we'll do that. And again, I'm going to tag it with a label so that we know that this job is running from this notebook if we see it somewhere. The job is going to go to BQ, load table from URI. We feed it the location of the file, Google Cloud Storage bucket, gs:// This is all stuff we defined in the last video. The destination from up here, and use this job to do this. Let's run that. And then we can, what we see from the last time I ran this, when I was creating this job, it ran for about 12 seconds. This star will disappear on the cell when it's done, and we'll be able to see how long it took us this time. All right, that should be wrapping up. There we go. Let's take a look. And it took 14.2 seconds today. I mean, we can go over to BigQuery and look, but before we do that, let's just run a query and take a look at it. In this case, let's just select everything from that table, but limit it to 5 records, 5 rows. Run that query, and since I'm in Python, let's tell it to bring that back to a data frame, a pandas data frame that's local, and print that out. Those print really nicely inside Jupyter Notebooks as cells, so we can see here's rows 0 through 4, 5 rows that we limited it to. Columns are time, and then V1 through V28. We have a column called amount and then a column called class. That's that, is it fraud 1, is it not fraud 0? Amount of transactions 0. Again, we don't really know what the units and things mean in the V's. That's a restructured data set. Well, let's do the next thing. Let's take a look at it in BigQuery, and then let's come back over here and let's maybe review it and prepare it so we can use it for machine learning. So back in BigQuery, I'm going to just hit the refresh button on this page. And now I should see the data set with the table underneath it. I probably didn't need to click refresh there, but there's StatMike Demo 3. Underneath there, we're going to see a data set called fraud, and under there, we're going to see a table. And the table's name is fraud. And when we click on that, we'll get a nice Review of the schema, it identified time as an integer in this case. It just depends on how it was stored. Just because it's labeled time doesn't mean it's a hours, minutes, seconds. This could, if we went to that Kaggle page and reviewed, we would know, hey, this is number of seconds since something. Float for all these, and integer for the class, it was 0 or 1. My favorite tab here is the preview tab. It gives us the ability to scroll through and look at it, very much like we just did in the Jupyter Notebook. All right. So now that we've got that done, one of the first things I want to know is, I know my goal. I'm going to frame my ML problem that's going to happen in all of these workflows. Is I'm trying to predict fraud, not fraud, 1 or 0. The first thing that comes to my mind when I'm trying to predict something that's categorical, it's a classification, is what is the distribution of the training data, the rows I have, to those categories. Let's take a look at that. Let's select star from fraud.fraud. All right, let's store it in a data frame. Let's do this locally. I could run this as SQL queries directly in BigQuery, but I'm trying to show you a balance of working in BigQuery versus bringing data locally and using it. If you're in Python, bringing locally probably means a pandas data frame, and then using it, in this case, would be taking the data frame, taking the column class, and get value counts for that. So that'll take every unique value in the column and tell you how many times a row appeared with that. We see the result from the past run. Let's run it again. So we see this is what you would call pretty highly imbalanced. We don't just have half the rows non-fraudulent and half the rows fraudulent. This mimics what you would expect. There's, of all the transactions that happen on a credit card, very few are fraudulent. That's the trick of the problem, is identifying which of the few are fraudulent. In this case, the data set they've given us has 492 fraudulent cases, transactions, has 284,315 non-fraudulent ones. That imbalance is going to mean something when we get to modeling. So let's just catalog that in our head. When we build a model and we're creating loss functions and we're optimizing them, we have to pick an objective for that. And our decision on that objective is going to be driven by this little piece of information right here that we're just going to put away in the back of our head. So keep that there. There could have been multiple classes, known fraud, suspected fraud, not fraud. In the case of that, you have multi-class. Still, I want to know that balance of the buckets. It's a very important piece of information for my approach to modeling. What this would be supervised learning, I have a target, and classification, I'm trying to put things into categories. If I was looking at the amount of transactions and predicting that, that would be more of like a regression kind of problem where I have this numerical output and I'm projecting the value, predicting it. This is definitely classification, fraud, not fraud. All right, preparing the data for analysis. I see all those columns in the data. I want a couple of things added. Most services I can use will split the data into training data, testing data, validation data for me. I can even kind of direct it with percentages. I like to work in a community environment where this one table, I mean, the whole reason of using BigQuery is it's so easy to share it with the team. This data set might get used over and over and over, and I don't want to compare my logistic regression to someone else's and get caught up in the fact that we just had a different split on the data from train to test to validate. So I like to go ahead and create a column called splits that has that division in it. I also like it when data sets have an identifier that takes me to a row. In this case, I don't have things like, hey, account number, date. I don't have like a key that gets me to a row, so I'm going to create a field that's artificial that's called transaction ID that'll immediately identify a single row in this table, since I don't have that other key-like information to give it to me. The way I do that is a SQL query. I'm going to create a new table from the existing table, and I'm going to do it with a couple of SQL tricks. Create or replace fraud underscore prepped. So it's a new table with underscore prepped attached to the name. I'm going to first create a table called add ID that selects everything from the original table. And it uses this function called generate UUID, name it transaction ID, from the dataset fraud.fraud. This is a great function. It creates these unique identifiers. Every time it runs, it gives you a unique value that you can use for things like creating an ID for a row. Now that table is created, I'm going to do my final step for creating the underscore prepped one. I'm going to select everything from that table, but I'm going to use a case statement to create a splits column. The way I'm going to do that is I'm going to take that unique ID, transaction ID, and apply the function farm fingerprint to it. Now, farm fingerprint takes a value and always generates this big hashed integer thing that is unique as long as the input's the same. So if I ever give it the same transaction ID, farm fingerprint will give me the same output giant number. I'm going to take that giant number for the row ID, transaction ID, I'm going to divide it by 10 and keep the remainder. I'm going to take the absolute value of it, divide it by 10. With the mod function, I'll get the remainder. Now the remainder of a number divided by 10 will be 0, 1, 2, 3, 4, up to 9, 0 to 9. So I got the space of 10 small single-digit integers. If it's under 8, so 0 to 7, I will call it train. So I'm keeping 80% of the data for training, labeling it train. If it's under 9, well, I've already taken out 0 to 7, so under 9 is only 8. So 10% will get called validate. And then the rest, the things that had a 9 as a remainder, they'll get labeled as test. So I'll run this query. Okay, and that job will take about 8 seconds. Again, that's 250,000 rows with, 30-something columns, and I'm generating unique IDs and a splits column. Bytes processed was about 70 megabytes. Review the split. Now, I told it 80-10-10. What did it get? Since there's still some randomness to this, this is just going to select splits and counts from that table and present it to me in the groups by split. And what I'll see is about 9.93%, almost 10 is validate, almost 10 is test, and just slightly more than 80 is train. So I have this nice split, and anybody modeling in my team that hits this version of the table and uses the splits column will all be using the same training data, same validation data, and the same test data. I like that. And it also gives us a technique to use in all of our workflows. We can either use built-in split or we can use our pre-created splits. All right, let's take a review of the subset now of that prepped source. What does it look like? We have additional columns, transaction ID, look at those big old values, and splits. Okay, now if I go back to BigQuery, that same table would be added here if I refreshed. At this point, we're ready to leverage BigQuery, this table, for machine learning in a number of aspects. Before we jump into the workflows, before we exit this video, let's do a little bit of Q&A and see what comes up. All right, Q&A. What questions do we have for this work?
Hi, Mike. Do I have to use BigQuery as my data source?
Absolutely not. Depends on what modeling you're using and what APIs it has to get to different data sources. Very commonly, people store CSVs, JSON, Avro, Parquet, whatever in Google Cloud Storage buckets, and they have their algorithms read from those. I like BigQuery for a reason. It's very easy to share and collaborate. If people want to export, it's very easy. We did that back in video or Notebook 00. We took the public data set and offloaded it to a CSV. That same technique would have made it easy to make Parquet or Avro or other files like JSON. It Gives me a great place to do data prep. Notice I created that splits column. Everybody that hits that table is going to have that same splits column. It made it easy to create a transaction ID and back near the source. It gives me options when I want to plug in my machine learning algorithms to a source that might not be able to hold all the data. When we get to TensorFlow, we're going to use a BigQuery IO or TensorFlow IO's BigQuery reader to, as it combs through the data for each epoch and it goes through samples and batches, it's going to prefetch those batches from BigQuery in parallel and keep streams of them going so that the local memory never has to be big enough to hold the whole table. That's great because sometimes you're sizing your computing environments not for training, but just to hold the data. This prevents that aspect. So that's another reason why I love BigQuery. But do you have to? Absolutely not. I'm going to motivate why I do, and then also show that all of these algorithms and things we use, they can get data from almost anywhere. So that's really cool. All right, next question.
Can you give me an overview of BigQuery?
That's a great way to kind of wrap this video up. Let's talk about what is BigQuery from a ML practitioner's point of view. I'm not going to give an exhaustive overview of BigQuery, but I will give you how I view BigQuery, and you can augment that with additional information. It's been around for over a decade. There's tons of great info out there. Let's take a look at this presentation. I created this. This is an overview of the architecture of BigQuery from the point of view of what the work we do as practitioners of machine learning. What is it? Well, it's normally when you set up a warehouse or something, you start thinking about all these aspects, like how much data is it going to need to hold and how big your table is going to be and how many queries. Like, I just created transactions in split column, but what if 15 people were simultaneously doing things with that table and there were thousands of tables and my company had thousands of users and they were all doing things? I have to kind of build something to hold all of that capability and then stick data in it and wait until those jobs happen. Well, BigQuery eliminates that paradigm by just saying, well, data sits at rest in storage. Queries come in, and in a managed environment, they just go into these things called slots and they execute your request in milliseconds and return the result back to storage or to you on the other end of the client. That means you don't have to do any of that planning. It just automatically scales with you. Let's take a look at what that really means. So BigQuery separates storage, data sitting at rest, from compute, data being used. When it's sitting at rest in storage, it's highly durable, meaning hey, it's actually duplicated. Talk a little bit more about that. So I don't have to worry about losing bits and bytes and things and blocks. It's also, when I go to compute, it's a highly available cluster. How do I work with it? Well, I can stick batches in. Like we worked with the CSV in this example to put a big file in. Well, there's also APIs to allow you to stream individual records in with very low latency. So if your application requires you to load batches nightly or hourly or every couple of minutes, cool. If your application actually requires you to constantly update with new messages almost instantaneously, there's streaming mechanisms as well, and all that data comes together in a table like we've been looking at. They have the same mechanisms for getting data out. I can get batches out. There's even a read API that doesn't even require me to hit that SQL layer where I'm computing. I can get directly to the storage layer and just absorb data, even filtered data, directly from storage. That's low cost and very, very fast. And that's great for ML where you're just trying to suck training data into an application and start training. That storage API or that read API we talked about, that's actually the mechanism behind TensorFlow IO's BigQuery reader. You can also stream records back. Then on the other end, interacting with BigQuery, well, I showed you it in the Google Cloud Console where you have an editor, you can write SQL. But we went from a notebook using Python where we created a client and we worked with it. Well, those clients are available for REST. There's a command line one called BQ where you can do anything basically with BigQuery. But those client libraries have that higher level abstraction or interface for Python, Ruby, PHP, Node, Java, Go, and C#. So it's one of these things where it's so popular that it's become available from almost anywhere. That's another great aspect, because in your machine learning orchestration, you never know where you're going to need to get data from or send data to. BigQuery makes a great part of architectural options when you do that. When you execute a query, things called slots, these little green dots that look like CPU chips, those slots, you don't have to worry about them. This happens automatically, but they contain enough compute, CPU, enough RAM to do part of an operation, and they have the networking capability to very, very quickly read from the storage. Your job gets staged, and at each stage it decides how many slots it needs to handle the size of data or the complexity of the query that you're running, and it even exchanges data between slots. It has this in-memory shuffling thing that goes on. All right, external data. We talk about bringing data into BigQuery. BigQuery can actually kind of federate things. So you can have a table sitting, that CSV sitting in cloud storage. You could actually link to it so that when you query, it actually goes and kind of temporarily loads it, runs a query, and retrieves the result. You can do that with cloud storage, with Bigtable, with even Google Drive. You can federate queries, meaning where it actually takes the logic of the query and it goes through a translator and it runs it in the data source for databases like Cloud SQL and Cloud Spanner from Google. And then it will just retrieve the result back to your query. These are two great ways to make BigQuery extensible to other sources of information without necessarily storing them in BigQuery. And that comes in handy in machine learning, where you're trying to augment your data sources with additional pieces of information. When you load a table, our data centers at Google have these things called zones, where they're like physically separated firewalls with different power sources and things. And when you load a table, it automatically splits it into blocks, and different blocks get stored in different zones, and different tables get different storage on different disks and different machines. You don't have to orchestrate that or figure that out. That's happening automatically for you. A single table, when you store it, the reason why it's very, very quick, we talked about a CSV. Could you use a CSV? Yes, but you're going to be reading data maybe not as efficiently as BigQuery. When you store a table with BigQuery, its blocks become very logical. It uses a format that takes the columns and stores them independently. That means columnar storage. So if I were to run a select statement and only name 2 columns out of 100, it only has to read 2 columns. It doesn't have to read all 100. So I don't need things like select star unless I really want everything. So when I'm training, just select the features in the target column you want from the table and don't worry about the rest. And it doesn't even scan them or read them. Those columnar pieces can be partitioned. If you've got timestamp data or customer IDs, those things can be used as partitions so that individual days worth of data in partitions, or hours, or groups of customers can be stored in physically separate boxes, so that when you use a where statement in your SQL clause, it'll only scan the columns and the section of rows in a partition that you reference in the where statement, meaning pass over less data so you get a faster response to get the request you're asking for. And within those partitions, you can name cluster variables. Think of those like, hey, sort it by these things, so that if you do have to scan inside of a block, you only scan the sections that you need to get to the part you're asking for. Those are all very, very easy to do and set up. The next part about BigQuery is built-in machine learning. We're going to look at this in the notebook series 3 that has 2 parts. Directly in the SQL language, BigQuery allows you to inject things like, instead of create table, create model. Name a model type, linear regression, maybe a neural net, maybe a deep neural net. It allows you to do these and select columns and actually have it run algorithms for you, parameterized from a BigQuery SQL call. And then it creates assets in your data set that are models. You can click those and you can see evaluation information like ROC curves and precision recall curves and confusion matrices directly in the console interface. This opens up high-level ML to a wide range of business users without ever having to think about some of our unique workflows that take this to other techniques. You can do a lot directly in BigQuery. But at the moment you want to do custom modeling, well, BigQuery has all of these higher level APIs built. I talked a few times about TensorFlow IO, where it uses the storage read API to bring in the batches in parallel a few at a time and keep them cycling so that it doesn't need to hold all the data at once. We have that for Spark. Pandas, I think in this video I even showed bringing it to a Pandas data frame, but there's even built into Pandas a thing called GBQ, or it's Google BigQuery, bringing in a BigQuery data set directly to Pandas that way. There are a number of ways to interact with it otherwise also. These are all clickable links. I'll try to include this in the repository so you can get to it. This is why I pick BigQuery for these demos. But remember, you don't have to, but this makes it a really good choice for a big collaborative environment. All right, let's go back to here. I believe that's going to wrap up today's video. I don't see more Q&A. That means it's time for me to give my pitch. If you like this video, press the like button. It's like giving me a cookie. If you didn't like it, it's also okay to press the dislike button. Do you want more videos like this? If you hit subscribe, it's like a feedback mechanism for me that says do more of these and give more. And if you click the bell, you'll be alerted when I do that. Did this help you? Give a cookie to everybody else. Like, leave a comment that encourages others that this information could be helpful to them. And most importantly, if you have feedback, other workflows that this triggered for you that you would like me to do or work on together, if you have corrections or things that you think would have made this better, go to the GitHub repository, click issues at the top of the page, and drop a note in there, and we'll interact and we'll make this repository better almost instantly for future viewers. With that, I want to say thank you for your time and your feedback. Let's work together to make the practice of AI and ML more collaborative, accurate, and approachable to a wider and more well-connected audience. With that, have a great day.